You ever see a drone just hang perfectly still in the air, even with the wind blowing? Or wonder how a rover on Mars knows exactly where it is? Well, the secret isn't some flawless sensor. It's actually a brilliant piece of math that works like a brain, letting these machines see clearly in a world that's, well, fundamentally blurry. So let's pull back the curtain and demystify this thing. Here's how we're going to break it down. First, we'll get a feel for why robots live in a constant state of uncertainty. Then, we'll learn the language of probability they use to talk about it. From there, we'll build the elegant two-step dance of the Kalman filter, see where it hits a wall, and then discover the clever fix that makes it a powerhouse in the real world. All right, first things first, we have to really get our heads around the biggest challenge for any autonomous system, the fact that nothing is ever perfect. I mean, seriously, think about it. If you tell a robot to move forward exactly 1 meter, did it? Really? Maybe a wheel slipped a tiny bit. And if its GPS says it's right here, is it really there, down to the millimeter? The answer, in the real world, is pretty much always no. You see, all those tiny little errors, from sensor jitters to gusts of wind to slight imperfections in motors, they all add up. They create what you can think of as a fog of uncertainty. The robot's actual, true position is hiding somewhere in that fog, and its mission is to figure out the most likely place it could be. So, how on earth do you describe a fog using math? You can't just use a single number, right? You need something more sophisticated. And that's where our good old friend, the bell curve, makes its grand entrance. So, instead of making a single, bold claim like the robot is at position X, we use a Gaussian. This lets us say something way more honest, like the robot is most likely right here at the peak of the curve, but it could also reasonably be anywhere in this general area. The peak is our best guess, and the width of the curve, the variance, is how humble we are about that guess. A wide curve means we're not very sure. A narrow one means we're pretty confident. This slide just nails the difference. On the left, you have this fantasy world of perfect information, one single crisp dot. But on the right, that's where we live, a fuzzy cloud of possibility. And the Kalman filter is designed from the ground up to thrive in that world on the right. Now, why this particular shape? It's not random. There are 3 fantastic reasons. First, they're super simple. You only need 2 numbers, the mean and the variance, to describe one perfectly. Second, the math is incredibly fast, which is a must-have for a robot that needs to think in real time. And maybe coolest of all, it just so happens that when you add up a bunch of small, random errors, they naturally tend to form a Gaussian shape. It's like it's nature's favorite pattern for uncertainty. Okay, so we've got our language for describing this fuzzy world. Now, let's talk about the engine that puts that language to work. The Kalman filter is this beautiful, looping, 2-step process. It's really that simple at its core. It's a constant cycle of predicting where you think you're going to be, and then updating that belief when you get a fresh look from your sensors. Predict, then update, over and over again. Let's walk through it. Imagine an underwater drone, an AUV. It starts with a pretty good idea of where it is. Then it's told to move forward. So it predicts its new location. But because it knows its own motors aren't perfect, its certainty goes down. That Gaussian cloud of possibility gets bigger and wider. It becomes less sure of its exact position. Then comes the update. The AUV sends out a ping to a sonar beacon and gets a reading back that says you're about this far away. But here's the thing. That sensor reading is also uncertain. It has its own noise, its own Gaussian cloud. So now the robot is holding 2 fuzzy ideas in its head, its own fuzzy prediction and the sensor's fuzzy measurement. And here comes the magic, the absolute core genius of the Kalman filter. It takes those 2 fuzzy Gaussians, the one from the prediction and the one from the measurement, and mathematically combines them. And what happens when you merge 2 sources of uncertainty in this specific way? You get a new belief that is more certain than either of the original 2. The new Gaussian is sharper and narrower. Your final estimate is better than your prediction was, and it's better than your measurement was. It's incredible. And this isn't just some random mashup. It's mathematically optimal. The filter is smart. It actually looks at how wide each Gaussian is. If your prediction was really uncertain, but you get a super precise sensor reading, it's going to trust the sensor more. If your sensor is notoriously noisy, it's going to lean more on its prediction. It always finds the perfect weighted balance between the 2. So this sounds amazing, right? A perfect recipe for zeroing in on the truth. Predict, update, get smarter. But there's a catch, a big one. The real world isn't always made of simple, straight lines. You see, all that beautiful, clean math we just talked about, it works perfectly for what we call linear systems. Think of a simple high school equation like y equals 2x plus 4. If you feed a nice, clean Gaussian bell curve into that kind of equation, another nice, clean Gaussian bell curve comes out the other side. Everything stays predictable. But what about a robot arm that rotates? Or a car that turns a corner? The math for that kind of movement involves curves, sines, and cosines. And when you try to push a perfect Gaussian through a nonlinear function like that, it gets warped. It comes out the other side looking all twisted and weird, and it's not a Gaussian anymore. And just like that, our simple, elegant math completely breaks down. So what do? You can't just make the world linear. So instead, engineers came up with an incredibly clever workaround. And that brings us to the extended Kalman filter, or the EKF for short. The EKF has one big, brilliant idea. It says, okay, I can't handle the whole curve, but for just one tiny instant right where I think I am, I can pretend the curve is a straight line. It basically finds the tangent to the curve at its current best guess and uses that straight line approximation to do its math. It's a hack, but it's a genius hack. And you can see the difference right here. The classic Kalman filter uses simple linear matrices to model the world. The EKF, on the other hand, uses the actual nonlinear functions to make its main prediction. But then, and this is the key, it uses that straight line approximation calculated with something from calculus called a Jacobian just to figure out what happens to the uncertainty. It's the same predict-update soul, just with a new brain that can handle curves. So let's bring this all home and talk about why this mathematical journey really matters. So to recap our whole story, we started by facing the fact that uncertainty is just a part of life for a robot. We found a language, the Gaussian, to describe it precisely. We built the elegant predict-update loop of the Kalman filter to wrestle that uncertainty down. And then we gave it a superpower with the EKF, letting it handle the complex, curvy reality of our world. This whole process is basically the foundation of modern navigation and tracking. And I'm not exaggerating when I say the impact is just massive. Some version of this filter is running in literally thousands of devices you see and use. It's in your phone, blending GPS data with your motion sensors. It was on the Apollo command module, guiding astronauts to the moon. And it's on rovers exploring Mars and submersibles exploring the deep ocean right now. And that really leaves you with a final thought, doesn't it? It's such a powerful concept. By fully embracing uncertainty, by giving it a name and a shape, we can build systems that see through the fog with incredible clarity. So, now that we've taught machines how to navigate a world of doubt with such mathematical grace, what other messy, uncertain problems are we ready to solve next?